Hello, this is Jack Jackson. Today we're going to be introducing exponential functions. Now if you remember back one of our earlier units we talked about linear functions, and actually linear functions I would claim would be the most important and useful class of relations. So if you just study one kind of function it would probably be linear functions because they're very useful. They model a simple kind of formula, a simple kind of graph, and they do model a lot of real world situations. And a lot of situations even that aren't linear are modeled pretty closely by linear as long as you zoom in on a close enough piece of the graph. But the second most important class of relations is exponential relations. And both linear and exponential are two basic ways things grow. One of the punchlines here, I'll go ahead and just say it right up front, is linear functions we know are functions that have a constant rate of growth, and exponential functions have a constant percentage rate of growth. And so those are two different ways that functions could grow that are important. When we restricted a linear function to a domain of the whole numbers or the natural numbers, we called it an arithmetic sequence. And similarly, when we restrict the domain to the natural numbers or to the whole numbers for an exponential function, we'll call it a geometric sequence. And so we're going to develop exponential functions very, very similar way to the way we developed linear functions. In fact, these notes I'm going to give a side-by-side development. On the left is going to be linear functions in black, and on the right side will be exponential functions in blue. And we're going to develop these side-by-side. In fact, if you wanted to, you could use this lecture as a development of linear functions. Now, since we've already studied linear functions in my class, then this is a review for linear and a parallel development for exponential, but one could certainly study these from the beginning with this approach and study these at the same time. In fact, back in the linear functions section unit, what we started with was a Mind's Own active learning project dealing with blocks. And if you remember, what we did is we had a certain number of blocks, say 5 blocks, and then we added to it each time, like we added 2, and then we added 2 more, and added 2 more, and added 2 more. And we looked at that physically. We looked at it in terms of the graph, the formula, the table, physically with the blocks. And then we tried to describe all that in words. Well, if you remember back to that project, you also had a different scenario that wasn't linear. It was actually geometric. That's where you had a certain number of blocks, and to get the total number of blocks on the next step, you multiply by the same one, like multiply by 2 each time, for example. Now, hopefully, if we've already studied linear functions, you already know about that, but what we should be able to do is expand this to exponential. So, let's go back to that project for a second. If you haven't done the project, you really should go back and redo it or do it. I think I have a video that actually reviews the exponential portion of that project a bit, and actually the linear a little bit as well. So I would say look at that first, and then this kind of summarizes a lot of what you see there and extends a bit. So here, in both cases, we're going to let x represent the step number, and we are going to have a 0th step. You could start at the step 1 and go on, but I chose to let step 0 be the initial starting point, and we're going to do that. And y is going to be the total number of blocks in both cases. Also in both cases, y sub 0 is going to be 5, which is our initial number of blocks at step 0. We're going to pick a constant operator. In this case, the constant operator is going to be 3 in both cases. But the difference is, on the arithmetic sequence side, the linear side, addition is going to be the repeated operation, whereas on the blue side over here, the exponential or geometric sequence side, we're going to let multiplication be the repeated operation. So in other words, we're going to, on the arithmetic side, we're going to add 1 to the step number. We add m equals 3 to the total number of blocks each time. So we'll start with 5, then add 3, then add 3 more to that, add 3 more to that, and so forth. The next, on the blue side though, what we're going to do is we're still going to add 1 to the step number, just increase the step number, but we're going to multiply the number of blocks by b equals 3 to get the total number of blocks. M is the traditional letter used for how much we add each time, which we call the slope, and I use the letter B for base, and you'll see why I call it the base in the geometric side. So let's illustrate the steps. First we start with 5 blocks in both cases. Next we do whatever it says. On the left, we're going to add 3 more blocks, so we have a total of 8 blocks now. On the right, we're going to multiply the total by 3, which is going to give us 15 blocks. And this is one way you could arrange the blocks. The next step, on the arithmetic side, we're going to add another 3 blocks. So how many is that? Well, we had 8 in the previous, add 3 more, that's 11. On the right, we're going to multiply by 3 more, and now we're up to 45 blocks. And then here's the 4th step here. So we could write down those, or step 3. Okay? And so here we have the step number and the number of blocks. So the next question is, can we write a recursive, well, first of all, can we extend the table? Okay? So how do we extend the table? Well, we've got the table worked up so far. If we want to extend one more, on the left one we're going to just add, was it 3? Yeah, add 3 blocks. So we're going to add 1 to the step number, so the step number is going to be 4. And we add 3 to 14 to get 17 for the number of blocks. On the right, if you notice what we're doing is we're multiplying by 3 each time. So we're going to add 1 to the step number to get step 4, but then we're going to multiply 135 by 3, and that gives you 405. And then you're going to multiply by another 3, and another 3, and another 3. And on the right one, we're going to repeatedly multiply by 3 each time. On the left one, we're going to repeatedly add 3 each time. So notice that the one on the right is going to be growing quite a bit faster than the one on the left. So then we want to find a recursive formula. Now recall that a recursive formula will have 2 parts to it. The first part identifies the term of the sequence, some term of the sequence, say one, in other words, 1 point from the function, from the table, wherever. And the second one is a recursion relation that tells you how to get from one term to the next term. So it's sort of like climbing a ladder. Sort of 2 skills you need. You need to know how to get on the first rung, that's your initial condition, and then you know how to go from one rung to the next, that's your recursion relation. Notice that a recursive definition requires you to know an earlier term to get a later term. Most of the time that's the term right before it. So notice that we can see basically how do we get from one to the next. In the left one we add 3 to the previous term, in the right one we multiply by 3. That's how we did it, and you can see it written out there. So, if we want to find a particular x value here, like this one here, okay, or this one here, what do? Like we want to find the ninth x value, ninth y. It's 32 here. How do we find that? Well, we know it's the step 9, so we back up to step 1 lower step, step 8. Find its y, the y of, so this would be, 9 would be x. We go to 8, which is x minus 1. We find its y, which is 29. And then we add 3 to that to get the y here. Okay? Over here, similar thing. If we want to find the 8th, this 8th y here, we find the term number 8. We back up 1 to term number 7, that's x minus 1. Find its y, y of the x minus 1, and multiply, whoops, I should say multiply by 3 this time. Okay, so we want to multiply by 3. Okay, so what would be our recursive definition? Our recursive definition is, first of all, tell it what's y of 0, which is 5, in both cases. And then we tell it our recursion, that's our initial condition. Then our recursion relation is y of x equals y of x minus 1 plus 3. That's for the linear side, or arithmetic side. For the geometric, or exponential side, that would be y of x is y of x minus 1 times 3. So we replaced addition with multiplication. So in general, the recursion relation for an exponential, or let's do the linear first. The recursion relation for a linear or arithmetic sequence is y of x equals y of x minus 1 plus m, where m is this constant amount we're adding each time. or the recursion relation for a exponential or geometric is y of x equals y of x minus 1 times b, whatever b is. So now how about a non-recursive relation? Well, we know to do this, here's the key to finding this out. The first one is, of course, just given. That's 5. The next one, let's look on the arithmetic side. The next one, what we do is we take 5 and we add 3. Then the next one is 5 plus 3 plus 3 more. And then 5 plus 3 plus 3 plus 3 more to get to 14. And 5 plus 3 plus 3 plus 3 plus 3 to get the next one, and so forth. So we see that on this left side here, they're always, for the term, the y value, it's always 5 plus a bunch of 3's. Well, we have a shorthand notation for repeatedly adding the same thing over and over again. That's the basic definition of multiplication. So, we could think of these as 3 times 0 plus 5 to get 5, 3 times 1 plus 5 to get 8, 3 times 2 plus 5 to get 11, and so forth. And we see that the number in parentheses just counts how many 3's we added. But it also turns out to be the same as the step number. Okay? So, we'll come back to that in just a second. On the exponential side, everywhere you see addition in the left, we see multiplication in the right. So the first one's 5, the next one's 5 times 3, then 5 times 3 times 3. Then take that 5 times 3 times 3 times another 3 for the next, times another 3 for the next, and so forth. So every term, every y value, is just a 5 times a certain number of 3's. We also have a shorthand notation for repeated multiplication. It's called exponents. And so we can write all of these as 5 times 3 to some power. The power counts how many 3's we multiplied together. And it also turns out that the power is the term number x. So this allows us to come up with a formula. Y equals 3x plus 5 on the left. So notice that whatever's in parentheses is the x, so that's just y equals 3x plus 5. And in the right, it's always y equals 5 times 3 to the x power. It's the x is the exponent. By the way, that's why we call these exponential functions, is because of the exponent is the variable. So this is, on the left, this is the slope y-intercept form, or commonly called just the slope-intercept form of linear equation. Notice that 0, y sub 0 is the y-intercept on the graph, or your initial value, your term 0, basically, is your y0. And so the m, the coefficient of the x, is what we call the slope. The slope is the change in y, delta y. That is the change in y's here. Okay? Or it's the common or the difference in the y's. So m is the common difference. The difference is the same every time as long as the delta x is 1. And so that's what the slope is. The slope is how much we're adding each time. Now over here on this one, it should say base y-intercept. So the base is replaced by the y-intercept. The base is replaced by, the slope is replaced by base, but it's still y-intercept. So, of an exponential function. So it's y equals y sub 0 times b to the x power. Again, 0, y sub 0 is the y-intercept on the graph. And this time the base is the common ratio. That is, we're dividing one y by the previous y to find the base. And the fact that that's the same every time, that's what we're multiplying by each time. Sometimes some people will use the letter r in place of b for the common ratio. We're going to use b because it is the base of this exponential function. We're going to call it b and do that. We have something later on that we're going to use for r, and it's in all exponential functions there is an r that we're going to talk about, and it's not the same as b. They're related, but they're not the same. So I want to be sure that we do not use the letter r here. I want to use the letter b. And I've used the traditional letter m for slope. Although some people will use the letter d for common difference when they're talking about sequences. Now, can we modify these formulas so that they're centered at various points? And we can modify this. Look how we did this. On the left hand, we have a point-slope form, okay, of the linear equation. And of course, if it's at 0, the point-slope form is just y equals 3 times x minus 5. But we can take the same formula and write it as y equals 3 times parentheses x minus 1 plus 8. Notice that this has the 1 and the 8 in the formula, so it's centered up at the point 1, 8, I would say. So notice if you plug in 1, you get 1 minus 1 is 0, times 3 is 0, plus 8 is 8. So 1, 8 is certainly on that equation, and it does have the same formula. If you use the distributive property to expand that out, you get y equals 3x minus 3 plus 8, which reduces to y equals 3x minus 5. So you see that it is the same formula, or the same equation, in a different form. Okay, but it doesn't matter about whether picking up at centering at 1, 8, you could also center it at 2, 11 or 3, 14, and you can see that. So in general, what we have is, for a linear equation, we can have a point-slope form that is y equals m times x minus x1 plus y1. The x minus x1 is in parentheses, where m is a slope and x1, y1 is any point on the function. In a similar manner, you can do a point-base form for an exponential equation. It's y equals y1 times b to the power x minus x1. That's weird. Okay, here we go. Okay. Alright, so there's our basic formula. Again, b is the base this time, and again, x1, y1 is a point on the function. So let's check this out. For example, if we want to center this up at 115, we would write y equals 15 times 3 to the power x minus 1. So this is very useful if your initial term is, say, the first term, if you don't really have a 0th term. Or maybe we want to start at the third term, which is 3, 135. We happen to know that particular one. Then we could write y equals 135 times 3 to the power x minus 3. Check it out again. If you plug in x1 in place of x, you get x1 minus x1 is 0. b to the 0 is 1. And then 1 times y1 is y1. So it does go through the point x1, y1. For example, if you plug in 3 in this third formula, y equals 135 times 3 to the power x minus 3. 3 minus 3 is 0. 3 to the 0 is 1. 1 times 135 is 135. So in fact, it does go through the point 3, 135. And if you graph these, you will get the same thing, or we can manipulate these equations using properties of exponents, and you would see that they are all the same. So now what we want to do is, what if we have a sequence, and it's not so nice that it has a 0th term written down for us, and it's not so nice that we already have, all the x's going up by 1. In other words, what if we've got sort of spread out 2 or 3 terms, but they're not necessarily right next to each other in a sequence? Can we still figure out what it would be? Okay, whether it's geometric or arithmetic. So this is what we're going to do now. So notice here we have some terms, and we're given 3 terms. In the arithmetic case, we're given the 11th term is 3, the 14th term is 9, and the 18th term is 17. Or in other words, we're given 3 points on the function, 11, 3, 14, 9, and 18, 17. Okay? So look at what we've got here. We're going to focus on the linear side for just a minute. The delta x is 3 going from 11 to 14. In other words, there are 3 steps. From 11 to 12 is 1 step, 12 to 13 is the 2nd step, 13 to 14 is the 3rd step. And then from 14 to 18, there's actually 18 minus 14, which is 4 steps. 14 to 15 is 1 step, 15 to 16 is the 2nd step, 16 to 17, a 3rd step, and 17 to 18 is a 4th step. So what we notice is the amount that the y goes up from 3 to 9 is delta y, which is 9 minus 3 is 6. And then for the second time, delta y is 17 minus 9, which is 8. So the question is, how can we get from 3 to 9 in 3 steps, adding the same thing 3 times, and still turn out to be the same as adding 6 overall? And if it works out, then maybe the same number will be the number, if it is arithmetic, the same number will be what we would add in 4 steps to get 8. So look what we have here. We have, let's see here. In the first case, we have 3, and we want to add m, and then add another m, and add another m, and then end up at 9. We want to add the same m 3 times to get 9. Well, adding the same m 3 times is 3m. So we started with 3, and we added 3 m's to that, and we got 9. Well, if we try to solve this for m, we should be able to figure it out. Well, if we subtract 3 from both sides, we get 6 on the right side, and it eliminates that first 3 on the left. So the 3 steps have to add up to the 6. So that says 3 times m has to be 6. So divide both sides by 3, we get m has to be 2. Similarly, if we want to go from 9 to 17, we got to take 9 and add m, and m to get 17, or add 9 plus 4m, 4 m's, to get 17. Subtract 9 and we get 17 minus 9, which is our delta y, is 8. And we have our delta x is 4 times m, so 4m is 8, and so divide by 4, we get that. So notice in general what we have our y1, whatever it is, and we're adding delta x times m to that to get our y2. Solving for m, we do y2, we subtract y1 from both sides, and we get delta x times m is y2 minus y1, which is just delta y. And then we have delta x times m is delta y, so m is delta y over delta x. Typo. Delta y over delta x. So we have just discovered the general formula for the slope. It is delta y over delta x, or y2 minus y1 over delta x, or y2 minus y1 over x2 minus x1. So this is between any 2 points, x1, y1, and x2, y2. So to say between 2 successive points that we actually know in the table. Okay, and if this is the same between any 2 successive points, then we have an arithmetic sequence, if it's a sequence, or more generally a linear function. So arithmetic sequences are, sequences, I should say, have a constant slope, and this should be sequences as well. Okay, let's look at the same thing on the geometric side. So remember back on the arithmetic side, the slope was just delta y. The difference is in the y's if delta x is 1, but if it's not, we had to make an adjustment by dividing by delta x. Now on the other side, let's look what happens. Here's 1. Again, delta x is 3, delta x is 4 for the 2 steps. The x's are the same in both tables, but I've changed the y values. So the first time we look at the y2, not y2 minus y1, but y2 divided by y1 to figure that out. And in this case, 56 divided by 7 is 8. So we're multiplying 7 by 8 to get 56, but we want to break that up into actually 3 steps so that we multiply 7 by the base to get whatever the y is for y of 12, and then we multiply that by the same base to get y of 13, and multiply that by the same base, and that should give us 56. And a similar thing down here for the next one. So what we want is we want to be able to take 7, multiply by the base, then times the base, then times the base again to get 56. In other words, 7 times the base cubed needs to be 56. So the base cubed is 56, then divided by 7, which is 8. And of course, to solve for b, you take the reciprocal power of the 1/3 power, so it's base to the 1/3 or the cube root of 8, which is 2. Similarly, we have 56 times the base times the base times the base times the base. In other words, is 896. So in other words, 56 times b to the 4th power is 896. And so we do 896 divided by 56. And that's b to the 4th. Then we take the 4th root, or the 1/4 power. And again, it's 2. So look what we've got in general. We've got y1 times base to the power delta x has got to be y2. So we divide both sides by y1, and we get base to the power delta x is y2 divided by y1. And so then we have the base is y2 divided by y1 to the power 1 over delta x, or the delta x root. So that's our general formula for the base. The base was just y2 divided by y1 if delta x was 1, but if delta x is not 1, I have to make an adjustment. Now I want you to notice something right away here. When we look up here in this situation, everything is one level higher in the order of operations on the exponential side. What was addition in the arithmetic is multiplication in the geometric. When we have this set up here, everywhere you see a plus on the left, you're going to see a times on the right. Repeated addition, so you got addition here, you're starting with your initial term of 3, and then we're adding to that. Here we're starting with our initial term, and we're multiplying it. It's one level higher. Where we have, and that's our recursive definition. On the non-recursive definition, wherever we have our initial term, which is 5 here, on the left we're going to add to that. This is an implied multiplication in the middle here. And where this one has multiplication, on the left we have a power on the right. How do we find the slope? That constant operator, in this case a constant adder. We're going to add the same thing. We subtracted the y's. Well, one level higher than subtraction is division. So we're going to divide the y's over here. Now that worked when delta x is 1. What we just did is we looked at an adjustment. And the adjustment is we take our y's and subtract here. Here we divide our y's. Here on the slope, to fix it for where we have missing terms, we want to divide by delta x. One level higher than a division would be a root. And so here over here on the right, we take a delta x root, or 1 over delta x power. I went ahead and wrote it as a power rather than a root, because that's the way you're going to use it in your calculator. Now, just like on the left, if you find this slope, it's actually defined between any 2 points. It doesn't have to be a linear function to define the slope. You can define it between any 2 points. But it's the linear functions or arithmetic sequences that have a constant slope. So if you do this between successive points and it's the same every time, then in fact you get a linear function. On the other hand, though, on the right, if you can do this base. It's defined between any 2 points. Okay, just like the slope is defined between any 2 points. But if it's the same every time, that's exactly the ones that are exponential. And so this gives us a way to see if they are exponential or geometric. So here's some examples. Well, this is the same example. I've actually just worked out the numbers. Now, there was something missing. If you notice, we already figured out the slope on the left was 2, and the base on the right was 2. Again, I'm trying to keep things as parallel as possible. So we can use the point slope formula on the left, y equals m times parentheses x minus x1 close parentheses plus y1. We just plug in the slope is 2, plug in any point we want. I happen to choose the first point here at 11, 3, and we plug in 11 for x3 for y, and we have our equation. We can solve that, we can distribute and combine like terms if we want to get y equals 2x minus 19 if we'd rather have the slope y-intercept form, or just slope-intercept form that's called. On the right, we have the formula y equals y1 times b to the power x minus x1. That's the point-based form, and we already figured out the base was 2, and we can use the point 11, 7 here and put x1 as 11 and y1 as 7. And again, we can use the properties of exponents to write this in the y equals y0 times b to the x form if we want. So, how do we tell if it's exponential or linear? Well, to tell if it's linear, we compute the slope between successive points in the table by the formula y2 minus y1 over x2 minus x1. And if that's the case, then we use the formula y equals m times x minus x1 plus y1. Or we could just use the formula y equals mx plus y sub 0. An alternative way would be then plug in an x and y that you know and solve for the y0. That would give you the same thing. Okay. On the other hand, for the exponential, we compute the base each time, which is y2 divided by y1 to the 1 over delta x power. You do that between successive points in the table. If that's the same each time, that's an exponential function, and it has a formula like you see here below. Y equals y1 times b to the power x minus x1. So let's do this. What if I have 2 points? Well, we know that given 2 points, there's exactly one line that goes through those 2 points. Okay, for 2 points with 2 different x-coordinates, that's going to be a linear function. Okay, so let's find the formula for a linear function between 2, 5 and 4, 14. Well, we use this process just like we did. We label one x1, y1, the other x2, y2. We find the slope, which is delta y over delta x, or y2 minus y1 over x2 minus x1. So that's 45 minus 5 is 40, and 4 minus 2 is 2. 40 divided by 2 is 20. So the slope is 20. And then we use the formula y equals m times x minus x1 plus y1. And we plug in the point 2, 5 for x1, y1, and the slope 20. And so there it is in a point slope form centered at the point 2, 5. We could have used the point 4, 45 instead if we'd rather. Now if I distribute here, I get 20x minus 40 plus 5 is 20x minus 35. So y equals 20x minus 35 is the slope x-intercept form. If I took that and factored the 20 out, I would have the factored form, or the slope x-intercept form. Now on the right, we can find the formula for the linear function through not a linear, I want the exponential over here. Okay, and it turns out that just as you can take 2 different points with different x-coordinates, just like there's only one line through them, there's exactly one exponential function through the 2 points. And how are we going to do that? I can take these same 2 points and find the exponential function that goes through there. Again, they're labeled the same way. And again, we still figure out delta x, which is x2 minus x1. So that's 4 minus 2 is 2. But this time we're going to compute the base, which is y2 divided by y1 to the power 1 over delta x. So that's 45 divided by 5 is 9. Then we're going to raise that to the 1/2 power, which is 3. So the base is 3. And then we use the formula y equals y1 times b to the power x minus x1. So that's going to be, again, I use the point 2, 5. So put 5 in for y2 and 2 in for 5 in for y1, 2 in for x1. And then that's our formula, 5 times 3 to the power x minus 2. If we want, we can manipulate this a little bit. Notice our property of exponents. This is 3 to the negative 2 power times 3 to the x power will give us 3 to the x minus 2 power. Remember, you have 2 things you're multiplying with the same base. You keep the base and add the exponents. So 3 to the negative 2 is 1 over 3 squared, which is 1/9, times the 5 is 5/9. So you could write that as y equals 5/9 times 3 to the x. And that last form is the y-intercept base form. So it goes through the graph on the y-axis at 0, 5/9. And we're multiplying by 3 every time we add 1 to x. Whereas the one on the left, it's going through the point 0, negative 35, so it starts at negative 35, and every time we add 1 to x, we're adding 2 to the y. So let's graph these two things. So the 2xy equals 2x plus 5, or if you do it in sequence notation, you might write it as a sub k equals 2k plus 5. And we can see that we get dots that are actually in a straight line, but it's not a solid line because the domain here is only the whole numbers being a sequence. And so we do have a dot on the y-axis because I allowed a zeroth term. But then where our dots go, they don't go to the left of the y-axis, but they do go up and to the right forever. This is not a square scale, but you can see every time you go to the right one from one dot to the next, you're going to the right one, but then you're going up 2. Now on the right side, when we graph a sub k equals 5 times 2 to the k, every time, again it starts at 0, 5. It's a different scale on the one on the right. Again, not a square scale. But every time we go from one dot to the next, we're still going to the right one, but what we're doing is we're multiplying the y values by 2 to get the new distance from the x-axis, the new height above the x-axis. Notice this time it's not straight at all. These have a definite, the amounts of increase are increasing, so this is a, you can definitely see a concave up kind of a shape to this. Okay, now, so far we've been talking about sequences. So if you notice, my label at the top of the page has always said arithmetic sequences and geometric sequences. But now we can make an arithmetic sequence into a linear function if we extend the domain to be all reals, and a geometric sequence becomes exponential function if we extend to all reals. So let's do that. And now let's use our notation that we normally use for functions whose domain is all reals. So we use f of x equals 2x plus 5 for the left, and the one on the right we say f of x is 5 times 2 to the x power. And these do go on forever in both directions. So the one on the left, you see the domain is all real numbers, and so is the range. It's also all reals. And it's now, the graph is a nice solid line. And by the way, we name the one on the left linear functions based on this graph, because its graph is a straight line. Whereas the one on the right, we don't really name it after the graph, we name it after the formula. And the formula, where's the x? Where's the unknown, the variable? It is the exponent, so that's called an exponential. So we name exponential functions by their formula, we name linear functions after their graph. Okay, so let's see what characteristics we have of the exponentials. The domain's all reals. You can put any power you want for a positive. So remember, a positive to any power is a positive, no matter what the power is. And so this means you're never going to get a negative output, and we're multiplying by positive, so still it's going to be positive. So we get, in fact, the range is actually from 0 to infinity, not including 0. So the range is all positive numbers. It's a continuous concave up, increasing graph. Now this is if the base is bigger than 1, you're going to get this concave up, increasing shape. The next example, I'll show you one where the base is less than 1. Okay? 0, 5 is the y-intercept in both cases. And so we're doubling the height from any point. Here's the same graph. Well, a couple things else to notice. Here's the same graph on a square scale. You can see it on the left here, the linear one. From the grid, you can see every time you go to the right one, you go up 2. The one on the right, you can see every time you go to the right one, you're doubling the height. So 0, 5, 1, 10, 2, 20 is off the screen. But notice what happens when we go to the left. You put in -1. It's 5 times 2 to the -1, that's 5 halves. Then you got 5 fourths, 5 eighths, 5 sixteenths, 5 32nds. Each time you move to the left, you're dividing the y by 2. And so it gets halfway closer to, but never touching, the x-axis. So on the left, we have a horizontal asymptote of the x-axis. So this one, the exponential here with the base bigger than 1, has a horizontal asymptote of the x-axis, y equals 0 on the left, and it increases without bound on the right side. So let's do a couple of different ones here. If we let the constant operator be a negative here on the left, so we have a negative slope, we end up with a decreasing function. So every time we go to the right one, we're going down 3 in this case, and we start at 0, 2. Whereas on the one on the left, we're going to pick a base between 0 and 1, and so that gives us a base of 1/3 in this case. This says every time we go to the right one, we're going 1/3, we're multiplying the y value by 1/3. So notice it flips over the x-axis, basically, so that the asymptote is on the right. It's still concave up, it's still all connected, but still the domain is all real, still the range is only the positives, but this time it's decreasing. So this kind here we would call exponential decrease or exponential decay, and the other one we would call exponential increase. Okay, we have some exercises here. So how can you look at the table and see if it's linear or exponential? And I think I'm going to leave these for you to read on your own and skip ahead just a little bit here. So how can we interpret these things in context of a real-world situation? So first thing to notice is the slope is the rate of change. It's the change in y values divided by the change in x values. So it is a ratio of changes of output over input. So change in output over change in input. So this is a rate of change. Okay? Now it turns out that in exponential functions we actually get a relative rate of change. So r is going to be the relative rate of change. The relative rate of change is often given as a percent. So what do we mean by a relative rate of change? You mean the actual amount of change, delta y, divided by the original amount. So if it goes up $5, that's a $5 increase. Okay? But $5, if you started with 100, that would be a 5% increase. It's always a percentage of what you started with. So it's y2 minus y1 divided by y1. Distribute the y1, we get y2 over y1 minus y1 over y1. y1 over y1 is 1, and if delta x is 1, y2 over y1 is the base b. So we get this relationship that the relative rate of change r is b minus 1. Now this is what I'm going to use for the letter r. It's always this periodic relative rate of change. Okay? It's going to usually be given to you in a percentage form, and you're going to convert to decimal right away. But then we have this relationship that r is b minus 1. So I will never use r for the common ratio. The common ratio in an arithmetic or a geometric sequence is actually the base. But we get this relationship that the r is b minus 1, or b is 1 plus the rate. So if you don't remember anything else, this is what you should really remember. The slope between 2 points is the average rate of change in the output over that input, and the linear functions are functions with a constant rate of change. Relative or percentage rate of change between 2 points is r, which is b minus 1, and that's the exponential functions are functions with the constant relative or percentage rate of change. So here's an example, real-world example we're going to look at. So suppose you're hired into a new company. In fact, you're getting ready to choose between two companies. Pretend everything else is exactly equal, or maybe it's the same company and they just offer you two options for a salary. Either way, your initial salary is going to be $50,000, but your raises are guaranteed. Not something you usually get in a real-world situation, but let's just pretend here for a minute. And suppose the raises are guaranteed, and there's two different possibilities, and we'll read those in a second. Okay, so we have this one, well, we'll do it right here. This one on the left, raises are guaranteed to be $2,000 each year. And on the company, that's company L. Company E, raises are guaranteed to be 3.6% per year. So your raises in company E are given as a percentage of what your salary was the year before. And of course, the raise is the amount of increase, whereas you get a flat amount of increase, a flat raise each year for company L. So let's make some tables for this and formulas. Okay? Well, the fact that delta t, well, that t be which the years of experience, so we'll start with t equals 0 is your first year's salary when you have 0 experience. Okay? And go on from there. Okay, so delta t is 1, we have delta s is 2,000, and so the slope is 2,000 over 1, which is $2,000 a year. This is linear. And so it starts at 50,000, then you add 2,000, you're at 52,000, then 54,000, 56,000, and so forth. And that's your salary each year. And that is linear. And so the salary as a function of t is 2,000t plus 50,000. On the other hand, let's look at the exponential side, and it is exponential. When you have a constant percentage growth, that's exponential function. And so the formula we're going to use is y equals y sub 0 b to the x, but b is 1 plus r, so it's 1 plus r to the x. R is given to be 3.6%. It's growing, so it's positive r, so that's 0.036. So then you actually add that to the 1, you get 1.036 is your base. And so your salary as a function of time is 50,000 times 1.036 to the t. So 3.6% of 50,000 is 1,750. Add that on, so your next year's salary. The next time you earn 3% of your previous amount plus your previous amount, or in other words 1.036 times the previous amount to get the next one. That's exactly what happens with exponential. Now notice what happens here is kind of interesting because what we have is that the first year the salaries are the same, $50,000 both cases. In the second year, after you've had 1 year of experience, your salary is actually higher a little bit with the company on the left. And it stays higher for a while. Okay, but then what happens here, look at year 9, it's highlighted. In year 9, finally the company in Exponential Company over here catches up. And then look what happens after that. It starts to actually run off and leave the other one behind, so it gets considerably better. Okay? So, if you think about the shape of the graphs, that makes sense, because the graph shape of for a linear increase is straight, versus this one's curved up. Eventually, that curving up is going to catch up with the linear one, no matter how big the slope is. Okay? So which one's the better deal? Well, it depends on how long you're going to work. So what we want is to figure out how much it would be for the better deal, but we don't just need to find out when the salary is better, because if you stopped at year 9, even though your ending salary would be an extra $145, it doesn't make up for all those years that you were behind. So let's look at what your total salary would be. First of all, here's the individual salaries to graph, and it's a sequence, so they're graphed. And notice the linear ones in a straight line are the little blue pluses, but the other one that's curved up, they start the same. It's a little bit below for a while, the dots, but then they go up, and the last dot's too big to even fit on the screen. It's quite a bit higher. Now this one is, I used a spreadsheet like Excel, actually it was Excel, to not only figure out the salary each year, but then also the total salary thus far. So for example, to find starts at 50,000, to get the 102,000, I did 52 plus the 50. To get the 156, I did the sum of the first 3 years' salary, which is the same as the 102 plus the 54. And I went down and did the same thing on the other one. And I'm not trying to use any shortcut formulas here, I'm just using a bunch of addition here. And so if you'll look at year 13, after 13 years experience, it'll be your 14th year with the company, the salary is finally a little higher on the exponential side, the total cumulative salary. But then look what happens as you continue on, and here's 30 years down the line. It's considerably higher for the one on the right, and in fact, the longer you work, the bigger that gets, and the bigger the gap gets. So, if you're going to work 13 years or less through year 12 on the experience, then you're better off over here on the left side. Any of these numbers are the same or bigger than the corresponding numbers over here. But as soon as you get past that, year 13, which is really your 14th year, 13 years of experience, it's higher on the right side. So your basic idea is, well, decide how long you're going to stay with the company. If you're going to stay with it at least 13 years, then you're better off choosing plan on the plan E, let's say, as versus plan L. Okay, so I think that gives you a nice introduction to both linear and exponential functions, starting with arithmetic and geometric sequences, and then eventually extending on. We got to see that in terms of physically with the blocks. We got to see it numerically in table. We found recursive formula, non-recursive formula. We generalized what we wanted to do to get a general formula for the slope and the base, and the general formula for the equation. We did that. There's a general form. There's the point slope or the point base formula. We saw that we had 2 points. We can find an equation of a line or equation of a exponential function. Let me go ahead and